Okay, Matt.
Okay, so I'm gonna kind of treat this like a YouTube video that hopefully I can use for a classroom training session. Kind of have them take their eyes off of me, back onto me on the board. Today's subject is going to be the defect depth formula in radiography. However, I wanted to start with a brief introduction about myself. My name is Matthew Yeager. I am an ASNT, NDT level 3 in PT, RT, and VT. I have approximately 7 years of welding experience and approximately 7 years of inspection in NDT with a little bit of welding mixed in between. I work at Fodler in Rochester, New York. We make glass line pressure vessels and alloy pressure equipment. But back to the reason why we're here. The objective of this lesson is for you to become capable of distinguishing and calculating the depth of a defect while using radiography. By a show of hands, how many people have employed this technique in their practical application? Okay, so there's a few of us, good. So I'm going to start out here with this picture. Knowing my joint geometries and my types of welding, I can kind of predict the depth of this first picture's defect. We're looking top view on a radiography here. We can see a slag line towards the edge of the weld. So if I know my joint geometry and the type of welding that was performed, I can make a safe assumption that it's going to be between the second and third pass just by judging on that. So if we go over to picture number 2 here, it's a double V groove with multiple passes and an indication running right down the center of the weld. So that tells me in this plane, it could be anywhere in between here and there. This is when I would like to employ the defect depth formula. Just a short rundown on the formula itself. It's going to be DD equals T times DS divided by MS, which DD standing for depth defect and T for thickness of the material. DS is defect shift, and MS being the marker shift. There are other methods to use, such as stereoradiography or computed tomography, also additional techniques that may provide more detailed information on the depth. This is a good approximation of depth. For these other methods, there would be a tube shift distance and source to object distance to calculate the results involved in those formulas. We're not going to really get into those, but I'll give you another aspect. Over here is an example of the method we would take to produce such radiograph. We take one shot with a marker on the plate, and you know your defect. One shot at an angle. You adjust your tube, take a second shot. We're going to use the same film, but it's going to be applied with a half exposure. So whatever it takes to create one exposure on a radiograph, we're going to cut that in half, shoot it half the time, adjust the tube, and then we're going to shoot it again. And that'll give us the shift in our defect and in our marker. So I'm going to go with example problem number 1 here. I'm going to do it with you guys so we're all on the same page. We have a material thickness of 1 inch and the defect shifted 0.187 and the marker shifted 0.375 of an inch. So I'm going to give you guys a minute to calculate this example. But I did say I would do it with you, so we'll do it with you. 1 times 0.187 is going to be 0.187. And we're going to divide that by 0.375. That's going to give us an answer of 0.499. Now remember, this is from the film side of the object. So we're going to be a ½ inch in on this, approximately a ½ inch in on this 1 inch material. If you just give me a second, I'm going to write down the second example problem, and then I'll give you guys about 2 or 3 minutes to figure it out. The material is going to be 2 inches thick. The defect shifted 0.675. So defect shift 0.675, and the marker shift is going to be 0.875. What I want to know, and the purpose of the question, I want to know the depth of the defect from the top side of the material to the nearest thousandths. So I'll give you guys approximately 2 minutes to run through that if you'd like. How are we doing? Does anybody need more time? We're all set then? Okay, so I'm going to start out with that. It's going to be 2 times 0.675 divided by 0.875. It's going to give me 1.35 divided by 0.875. Which gives me an answer of 1.543. But we're not done, right? We want the top side of the, from the top side of the material. So we're going to go 2 inches minus 1.543, giving us an end result of 0.457 from the top side of the material. Did anybody get that answer? Good job. Nice. Before I go into my closing, I just would like to reference this material as a mathematical formulas and references for non-destructive testing and radiography. 4th edition by J. Mark Davis. That's where I got my formula and my first example problem. I would like to thank you for your attention and the opportunity to present this topic to you, and it should prove to be beneficial in further operation or practical use. Were there any questions, comments, or concerns? Nope. Thanks for your time.
Yeah, I thought you explained that pretty clearly. Everybody got the answer that Matt was looking for? Are you doing this on every weld, looking for the depth on that, or using this formula all the time?
That was something I left out. I don't use this formula very often. I don't typically have a need for it because the material thicknesses that I deal with, it doesn't really require the application of the formula. Sometimes there's better options such as UT to go and get an exact depth for this.
Yeah, I just had another quick question for you. I mean, since we're going to be doing a math course here, a math refresher.
Sure.
How much math are your level 2 technicians doing in the field or in the shop?
I would say it's, it happens. It's not very often, but you do have to calculate in radiography your UG factor, Sometimes you might want to change your shot distance, so you have to employ a formula for changing your shot distances. Also, if you want to change the density, you can, there's another calculation for changing the density as far as time or milliamperage exposure.
I know a lot of machines, and maybe not radiography, but UT and ET, they do all the calculations for you.
There are some aids when using exposure times. There are charts,
Okay,
exposure charts. There are slide rules for gamma ray sources that can help you approximate your time. And most of the time it is an approximation. It's not going to be exact, but it'll
Okay.
get you in the ballpark.
other questions for Matt? All right, another round of applause for Matt. Thanks, Matt.